All right, welcome back. This video is about a method of integration called integration by parts. Before getting to integration by parts, I want to show why it's necessary, and we'll do that by first looking at integrals that don't need integration by parts. For example, the integral or antiderivative of the cosine of 2x can be found using substitution. So I would let w equal 2x, and that means dw by dx, the derivative of our substitution, is 2, and this can be rearranged to obtain dx, which is equal to dw over 2. I'm going to use that to replace the dx inside the integral. Now my integrand becomes cosine of w. My differential becomes dw over 2. And then I can rewrite that 1/2 integral of cosine of w dw. We can complete this antiderivative. Antiderivative of cosine of w is sine of w plus c. And then we can undo the substitution. I can replace w with what it originally was, 2x. Okay, that'll be our answer. Now the reason why substitution was used is we are reversing a chain rule. When we take the derivative of the sine of 2x, we have cos of 2x multiplied by the derivative of the inside. So we're running that process backwards. Use substitution to reverse a chain rule. Here's another example. We'll solve this one the same way. I recognize that the x that's outside the cosine of x squared, that is a constant multiple of the derivative of x squared. Derivative of x squared is 2x. So there's this relationship between the different components of the function. The part that's being plugged into one part of the function can be related, or rather its derivative can be related to another part of the expression. That's usually a signature that the integral can be completed using substitution. So I'm going to let w equal what's being plugged in. X squared is being plugged into the cosine function. I know I'm eventually going to have to get an expression that's equivalent to dx, so I'm going to take the derivative of the substitution and rearrange it to get dx, and dx is dw divided by 2x. So I'll plug that in for the differential. The new integrand still has an x in it temporarily, and then we have the cosine of w multiplied by our replacement for dx, which is dw over 2x. This substitution, we can tell right away, is appropriate because the old variable x disappears completely. We have an x on top and x on the bottom, they cancel out. And we've done this before, this isn't new, but I'm going through it again to contrast with what happens when this doesn't work. Okay, so go through, take the antiderivative, and then undo the substitution. Replace the w with x squared, and that's our answer. And again, we are undoing the chain rule. Using substitution. All right, let's try this same thing here. X times the cos of x. So, we have an x being plugged into the cosine function. So I'm going to let w equal x. Then dw by dx is equal to 1. So dx is equal to dw. So now we have the w replaces that x, the w replaces the next x, and the dw replaces the dx. And we've made no progress. No progress has been made. Sometimes when we use substitution, this happens. Essentially nothing happens. Maybe we'll get it multiplied by a constant. Say if it wasn't an x inside the cosine, what if it was 3x inside the cosine? So we would have some different constants floating around there. In other instances, the substitution will make it worse. So we'll go from an expression that we can't take the antiderivative of to an expression that is even more complicated, is even harder to imagine the antiderivative of. When this type of thing happens, it means that our method is bad. Our method is not appropriate for that particular problem. So we need a new method. After the lesson, you'll be able to answer these two questions. You'll be able to answer what is the antiderivative of the ln of x. It's not 1 over x, that's the derivative of ln of x. And you'll be able to answer the question, what is the antiderivative of x multiplied by e to the x? So keep these in mind. Come back and do these on your own later. Before proceeding with integration by parts, I want to review taking derivatives, in particular looking for product rules. Integration by parts is directly connected to product rules, so I think going through this is important. First function I want to take the derivative of is x times ln of x minus x. Now for the first part of this expression, there's two functions multiplied together. X, which I'll call capital A, and ln of x, which I'll call capital B. So we're preparing to do a product rule here. So I'll write down the derivative in terms of that product rule. We'll have a times b prime plus b times a prime. And then there's a lonely x all by itself on the right hand side. It's not involved in that product rule. It's just a separate derivative. The derivative of 1 times x to the power of 1 is just 1. All right, so let's keep going. Let's take the derivative of the first term there. So a times b prime, we have x times the derivative of ln of x, which is 1 over x, plus b, ln of x, multiplied by the derivative of x, which is 1, minus the lonely 1 that was already there. Now we can simplify. X times 1 over x is x over x, which is 1. Ln of x times 1 is just ln of x. We got the subtraction of 1, and look what happens. We get ln of x. That indirectly answers the question on the last slide. What do you think about that? In the next problem, let's take the derivative of x times sine of x plus cosine of x. We have a product rule in the first two terms. Once again, we have an a and a b. I'll call x the a, sine of x, I'll call that the b. And then the cosine of x off on its own, separated by the plus sign, does not get involved in the product rule. It's just a separate derivative. So we'll have a times b prime plus b times a prime. And then we have the derivative of cosine of x, which is negative sine of x. Now I'll fill in the product rule parts. A times b prime, so x times the cosine of x plus sine of x times 1 minus sine of x. Look what happens here. We have a sine of x minus a sine of x. Those cancel each other out. We just get x times the cosine of x. And that indirectly answers one of the questions that was asked earlier. What is the antiderivative of x times the cosine of x? And the answer is x times the sine of x plus the cos of x plus c. This is not the way to do antiderivatives of these expressions, though. Like, this starts with the answer and basically asks you to verify that the derivative of the answer gives you the function. So I'll state that explicitly here for the second one, and I want you to think about what the first one says in this context. This second one, this means that the integral of x times the cos of x dx is equal to x times the sine of x plus the cosine of x plus c. We're just verifying that that is the solution. And it's helpful to think about this relationship between derivatives and antiderivatives all the way through this component of calculus. That when you take the derivative of, let's say, little f of x, oh, do I have these reversed? I got these reversed. I gotta fix these. I shouldn't even have those there. That's just confusing. Okay. Let's not label them. So what we have is this type of opposite relationship between the derivative operation and the antiderivative operation. When you take the derivative of sine of x, you get cosine. Then if you take the antiderivative of cosine, you'll get sine. If you take the derivative of x squared, you get 2x. If you take the antiderivative of 2x, you get x squared. So if you go back to those two examples, the derivative of x sine of x plus cosine of x being x times the cosine of x, that tells us that the antiderivative of x cos of x is x sine of x plus cosine of x. And the one that's up above is a similar statement. The derivative of x ln of x minus x yielding ln of x tells you that the antiderivative of ln of x is x ln of x minus x. But again, this isn't how you would integrate, because this starts with the answer. You want to be able to obtain the answer without knowing it, without knowing what it is. Before I show you this method of integration by parts, in order that allows you to get these answers without, to get the answer without knowing the answer, I want to emphasize this aspect of anti-differentiation and integration that allows you to check your answer. As your number of methods for taking an antiderivative, as the number of methods grows, it becomes more important to be able to validate that what you're getting is actually the solution, and that you did not make a mistake. So in this example, that's what we're doing. We're asked which of the following is the outcome of the antiderivative of x times sine of x. So to do that, to figure out which one it is, we have to test each one. Check each to determine d by dx of what is equal to x times the sine of x. So which one of these do you take the derivative of that will give you x times the sine of x, and that will be the answer. So I'm going to take the derivative of each option. The first one, d by dx of x times the cosine of x minus the cosine of x plus c. So I have a product rule in the first term. We'll have x times negative sine of x plus cosine of x times 1 minus negative sine of x plus 0. So those first two terms came from our product rule, just like what we already did. And then we can simplify. We get negative x sine of x plus cosine of x plus sine of x. And this is not right. This is wrong. This does not equal x sine of x. So we can cross out option A. Now we do option B. d by dx of negative x sine of x plus cosine of x plus c. So I get another product rule. So the first function times the derivative of the second. We can tell right away that, well, maybe not, but I can tell right away this isn't going to work, but maybe you can't yet. So let's keep going. And then we have the second part of the product rule, sine of x times the derivative of negative x, which is negative 1, and then minus sine of x plus 0. So instead of having x times sine of x, we have x times cos of x. And these two terms that we have at the end here don't cancel. So lots of problems with this one. It's not equal to x sine of x. That's the most important thing. So we can cross it off from our list. That means C must be the answer. Well, let's confirm. Let's confirm by taking the derivative and making sure that it matches and that I didn't give you a defective question. So d by dx of negative x times the cosine of x plus the sine of x plus c is equal to, well, I should label the product rule that's being used. So we'll have a times b prime, negative x times the derivative of cosine, which is negative sine of x, plus b times a prime, cos of x times negative 1. Now we have the derivative of sine of x, which is cosine of x, and then plus 0. The negatives in the first term cancel, negative and negative positive, so x sine of x minus cosine of x plus cosine of x. Well, those last two terms cancel, so we get x times the sine of x as needed. So that's just checking your answer. That's, given a list of functions, can you determine which one is the antiderivative of the target? Now for the product, or for the anti-product rule, also called integration by parts. The notation's a bit weird. With substitution, I use the letter w. Let w equal some component of the expression. With integration by parts, I'm going to use the letters u and v instead. They're going to play a similar kind of role. With substitution, what we did was we transformed one antiderivative into another antiderivative in terms of a new variable. With integration by parts, we're going to transform the integral, but it's going to still be in terms of the original variable, usually x. So keep that in mind as we go through this, that there is this similarity and introducing another letter that represents part of the function, but philosophically, we're not changing the x-axis. We are rewriting the expression. It will still be in terms of x. So this u and v thing that we're about to do is temporary. It's not going to stay with the calculation at the end. Anyway, I want to rewrite our product rule that we've been using. We've been using it in terms of capital A and capital B, but that's arbitrary. There's nothing special about the letter A, nothing special about the letter B. We could have been writing it in terms of u and v. So the product rule, the derivative of u times v would be uv prime plus vu prime. V prime we can write as dv by dx, and u prime we can write as du by dx. So I've just rewritten the product rule using this notation. The next thing I'm going to do is I'm going to take the first part of this expression and the second part of the expression and just write them side by side. So d by dx of u times v is equal to u dv by dx plus v du by dx. The next thing I'm going to do is I'm going to take the antiderivative of both sides with respect to x. So the antiderivative of the derivative with respect to x of the left side is equal to I'm going to fill in the purple right now, antiderivative of the right-hand side with respect to x. So I have to do the same thing to both sides. If I take the antiderivative of one side, I have to take the antiderivative of the other side. They're both anti-differentiated with respect to the x variable, so that's indicated with the dx. Now, we know that the antiderivative of the derivative, those are opposite operations. If I take the derivative of 2x and then take the antiderivative, if I take the derivative of x squared and then take the antiderivative of that, so the antiderivative of 2x, I'm going to get my x squared back. And it doesn't matter what function I put there. If I do both of those operations in that order, I'm going to get no change. So I'm going to get u times v here. That's the original function I'm taking the antiderivative of, is equal to. Now on the right hand side, I'm going to split this up as two integrals. First part times dx plus the second part times dx. And then in each of those pieces, I'm going to cancel out the dx. So we get integral of u dv plus the integral of v du. Now comes the part that may not look like anything to you right now. It may look like just manipulations with no purpose. Oh, I canceled the wrong thing in there. I should cancel the dx with the dx, not the dx with the du. Okay. I'm going to subtract the integral of v du from both sides. So thus, the integral of u dv is equal to uv minus the integral of v du. That's your formula. Like I said, it doesn't look like anything. But what it does is it allows us to run the product rule in reverse. It allows us to identify that some function, its antiderivative, is going to be another function whose derivative requires a product rule. And we can identify what one part of that product rule derivative would be. And what's a good way to put this? I guess what this is doing philosophically is it's replacing the integral that we're starting with, which I should mention that the one on the left hand side is what we start with. So that represents our starting integral of u dv. We're going to rewrite it as a function, uv, minus a different integral of v du. And the hope is that by doing this, we'll have a nicer expression. We'll have an easier integral on the right-hand side than we have on the left-hand side. And we'll stop here, and I'll continue showing you how to use this formula with some examples in the next videos.